Consider the following problem. Charges Q1 and Q2 are separated by some separation A. We're assuming that these two charges are both positive and that they're held in place by some other force or agent that otherwise does not impact this problem. We also have a green X, a distance B from Q2, and this are perpendicular to each other. Okay, so here's the problem. We place a third positive charge, little q, at the location of this X, at this green X. It's initially at rest. Now, of course, little charge q, being positive, is repelled by these two positive charges and flies off and just keeps going until it's infinitely far away. The question is, how fast is little charge q moving when it is really, really far away? That is, when it's infinitely far away from the other charges. And we're told to ignore all non-electrical interactions in this problem. Okay, so how are we going to solve this problem? Well, we might think, okay, let's find the force that Q1 exerts on the little charge Q that we place here, and find the force that Q2 exerts on the little charge Q that we place here. Add those forces up as vectors, divide by the mass of little charge Q, and we could then find the acceleration of that little charge Q. Of course, as the little charge Q moves further away, it's going to have different distances, different forces. We've got to calculate the acceleration again, and we're going to have a big mess. So we're going to have to find some other way to get an analytical solution. Well, one thing we can do is note that the electrical interaction is a conservative interaction, and so that puts energy methods in play. And so that's what we're going to use. We're going to use conservation of energy to help us solve this problem. Let's see how that works out. First, we need to consider a system. Well, now, charge 1 and charge 2, Q1 and Q2, they're held in place by some other agent, but we are told that that other agent or force doesn't otherwise interact with this problem. So maybe we can consider a system consisting of charge Q1, charge Q2, and the charge little q that we're going to put right here. So that's going to be our system. Now, we're told to ignore all non-electrical interactions in this problem, so that basically leaves the interaction of Q1 with the little charge Q, Q2 with the little charge Q. Of course, Q1 and Q2 are interacting with each other, but not a lot's changing there. Great. So we can consider this system of Q1, Q2, and the little charge little q that we place right here to be an effectively isolated system for energy purposes. And we know that the change in energy of an isolated system is 0. The change in energy of the system will consist of the change of the kinetic energy of this little charge q and the change of this little charge q's potential energy as it moves in the electric potential of these two other charges, Q1 and Q2. So let's expand this out using the formula for kinetic energy right here. We can note that the initial kinetic energy is 0 because this charge Q is initially at rest when we place it at the X. And then we can solve for the final speed, V sub f, of the little charge Q when it is really, really, really far away. Now, in order to get any further, we need to know the change in potential that this charge little q moves through as it goes from the green X to infinitely far away. But the potential at infinity is 0, so the change in potential is just the negative of the initial potential. The initial potential, which is just the electric potential at this green X, is the potential at green X due to charge 1 plus the potential at the green X due to charge 2. And we can just simply add those up as regular numbers because the electric potential is a scalar. Putting this all together and substituting in for the change in potential, we get our formula for the final speed, that is the speed of the charge q when it's infinitely far away from the other charges. Let's do some reality checking with this result. First of all, we expect a greater speed for greater amounts of charge Q1, Q2, and little q, because the greater they are, the greater the repulsion, and we see that here. If this, and this are bigger, we get a greater final speed. Also, the smaller the mass, the greater the mass, the smaller the final speed, because it'll be harder to accelerate a large mass with a given amount of potential energy change. All right, also these numbers are important. If A and B start out really big, then these terms become smaller. That means there's less amount of distance over which the electrical force can push little charge Q from where it starts to infinity. So that makes sense that there would be a lower final speed if A and B are large. So there's all that checks out. Finally, we can check the units. So note that the electrical constant K times Q times another Q divided by units of distance, so that's either here or here. That gives us units of energy. Units of energy divided by units of mass, so joules divided by kilograms, gives us meters squared per second squared. If we take the square root of that, we get units of meters per second, and that checks out, of course, if we're looking for a final speed. So our result looks reasonable. It has the right units. We can be reasonably confident that it's correct.